Hope that y'all enjoyed your break. Um, for this week, I'm going to use today and Wednesday to close out our integration that we've been talking about in antiderivatives. And then the plan for Friday is just kind of an open review day. I'll make sure to do as best I can to be available from 8:30 all the way through class time on Friday for any questions you have for next week's final. I hope that you did see my second announcement I posted today, though, that our final, if I remember, I was scheduled for Wednesday the 10th from 11:30 until 1:30. Okay, so it starts a little bit later and it's a 2 hour time slot. So keep that in mind and make your plans accordingly. Now, as far as dealing with integration, the one thing we wanted to talk about was this idea of having the aspect of an antiderivative. So undoing a derivative is one part of it, but also dealing with this from the perspective of like areas and stuff. Yeah, the final will be in our normal classroom. It's just will, like I said, it's not the normal time. That's the part you have to be careful of. Now, as far as this new section is concerned, I'm just kind of building from what we talked about. What was it last Monday and the week before a little bit. As far as this problem is concerned, though, what I want us to see is, hey, we're going to be looking at this as an integral, but we're going to use what we call a definite integral. We have some boundary values here. We're going to go from x is -3 all the way to x is +3 of this function. Okay. Now, with that in place, make sure you look at this from a perspective of a graph. So if I plug in 0, 9 minus 0, and then the square root of 9 is where I'm going to get that point from. So know that I'm just plugging in x values here. Other great x values to plug in would be -3 and 3. Those are nice because, hey, 3 squared is 9. So I'll get that. Some of you might recognize this from college algebra. This is the equation of a circle, specifically the upper half of a circle. So not just any circle, a semicircle. Okay. Now, what a definite integral helps us with, right, is evaluating to get to specific results. One of those results is an area under the curve. So with this definite integral, what we're trying to find right here is what's going on underneath this curve and between the curve and the x-axis. Okay, so keep in mind when I say under the curve, the x-axis represents the bottom part of that area. Now, as far as integration is concerned, you run into issues where you're not always able to work it out in a nice way. Okay. I'll try my best to make sure to talk about a couple of those examples as we go through the next couple of days. Um, but this right here would be an example of where technically we need some other things to work through this. Okay. The problem you run into when you look at this function is, hey, we have a radical. So if we wanted to, we can use this rational exponent approach, but that x squared on the inside makes it kind of a little bit more involved. Okay. As time permits today and tomorrow, we'll definitely talk about some that we can work on and others that, hey, we would need advanced techniques. Okay. Now, as far as this one is concerned, though, this will give us that area under the curve. Well, the nice thing about this area that we just talked about, that's just a semicircle. It's pi r squared divided by 2. And I just wanted to connect this back to what we talked about last time, where we looked at it like, hey, I have a line, I can create a triangle. If you have a horizontal line, you can create a rectangle, and we can use that kind of moving forward. Okay. Just make sure you see here, as far as this circle is concerned, the radius is one part we need to have. The good news is you can always just use the intercepts that you have there. So from the origin to an intercept, hey, that's just a length of 3. So the area of this would be pi times 3 squared all over 2, or 9 halves pi. Now, as far as dealing with pi, just know that typically we'll use like 3.14 as far as that value is concerned. If you wanted to plug that into your calculator and get a decimal, Not something we run into all the time, but since we have a circle here, if you have a sphere or cylinder, make sure you're ready for pi. I would say typically we'll be safe using 3.14 unless a problem states otherwise. So what we find here is, hey, when I go through this problem and I deal with this integration, if I use that f of b minus f of a approach I kind of briefly introduced last week, we're going to get that same value, 9 halves pi. I know I went through that a little bit quicker. So are there any questions? I just want to make sure to connect it back and show like, hey, it's a semicircle. Fun stuff. Okay, so the next step then is to kind of build from there. All right, so this next problem here you'll see is a quadratic. All right, so what if we're looking at this function and we need to find the area under the curve for whatever reason? Make sure you see here though, this quadratic has some issues that we have to discuss. Now I'm just going to do a quick sketch of this, but if we go look at this function here, if you remember with this one here, first we'll be able to put something at the point 16 here for our y-intercept. So 0, 16 is our y-intercept. And from there, we would draw our graph going downwards. Okay. Now, as far as dealing with these areas, things are definitely going to be needed. So that's where intervals were important. So as you saw with my last one here, I gave you an interval here that says, hey, this is what we're focused on. Okay. We could definitely do what we called indefinite integrals and just say, hey, what is this going to give us if we look at it from the perspective of an indefinite integral? So one of the things we have looked at is just the fact that, hey, we can use some of the properties that we've seen previously, but now we're working backwards. We're not trying to find a derivative here, but we're working backwards. So like for 16 here, hey, that would become 16x. For the x squared, I would have 1/3 x cubed. Now, when we're dealing with derivatives and such, not derivatives, sorry, integrals and such, don't forget that we will need to put a plus c. So if I just ask you to, hey, find the indefinite integral for this particular problem, that's what our work would look like. The next step, though, if we want to talk about this, like say we're trying to find the area under the curve between our x-intercepts, for instance, this is where those intervals will become very important. An upper bound and a lower bound will need to be given for whatever purpose we're trying to work with. Sometimes you're going to have to find the upper bound and lower bound. Sometimes they'll give it to you. It's like here, if we're looking in between our x-intercepts, we would say, hey, we're going to be going from -4 to 4. And the idea there is, hey, 4 squared is 16, 16 minus 16 is 0. So that's why I'm picking the 4s. Now, what would do differently for our integral then is say, hey, I'm going to put those boundary values here and then deal with it from the perspective of the integral. Now, the good news is we've kind of talked about the antiderivative perspective. So we have that in place, but the problem here is what's going on with the area. Let's make sure we look at that. If I focus on this and kind of get rid of these other pieces, what you're going to find here is I can't really use geometry directly like we did the previous problem. This one was nice because, hey, that I got that from the equation of a circle, specifically the upper portion of the circle. So technically a circle would have a plus or minus here, and I just used the positive. So that worked out nicely. As we begin to look at other shapes, that's not always going to work out as nice. So what happens is we have to use approximations to do that. Now, we're not going to spend a lot of time with the approximations. There's going to be some of your homework to look at. My main thing is just make sure you understand it's out there and that, hey, it's kind of needed to bridge the gap. All right. There's some things like in limits we didn't dive into deeply that kind of help us with different perspectives. Hopefully, you saw that like when we're talking about rational functions. Hey, the limit is definitely helpful here. So make sure we understand it. But we still could just know that that's a vertical asymptote, for instance, with the rational function. Here, what you need to see is if I zoom in on this graph. So if I just kind of use more of a general quadratic, and let's just look at the first quadrant to help us. So we have a y-intercept, an x-intercept, and the graph kind of does one of these. All right. One way to build approximations is using rectangles. And the idea behind this is we're going to pick an endpoint. So let's say, hey, let's start here. And then let's just draw rectangles of equal width. So when I say that, I'll go down here and say, hey, I'm going to draw a rectangle. The width of that rectangle is 1. We're then going to go up to this intersection here and then draw another rectangle and just make sure that we keep building rectangles that have that same width. Of course, we would go from the starting point to the ending point. Now, the reason I use the word approximation here, though, is if you take this approach, you're going to have oftentimes an overestimation or an underestimation. So you'll see like these little pieces I'm circling here are outside of our actual graph. So they're great for approximations, but that's what they're good for is an approximation. Okay. The good news is we have ways to build stuff to give us a more exact approach. And this is where limits definitely become important. So you'll see here a good definition. Oh, I don't know why I did that, y'all. But as I was saying, here we have a nice little definition that we can use to get from those approximations to how can we use the definite integral to get not just any area, but the exact area. So keep in mind, as I said, with the rectangles, it's an approximation, but this is going to give us the exact area. Now, some things we do need to point out is that our function has some limitations, and specifically it has to be continuous for this to work. That's one thing you always have to watch for. We've talked about being continuous, something has to be differentiable. Those are things that are definitely important. Now, the other thing we're going to look at is we're looking at a definite integral. So we have a specific closed interval we're focused on. All right. And we're going to be looking at those rectangles. So what you'll see here, that's going to be the length and the width down here. So you see one value times another value. Those are going to be our rectangles, length times width. Now, things to take from this statement, if you haven't seen it before, is what we call summations. So like if I said, hey, let's just do the summation from I equals 1 to 4 of I. We have a little bit more going on down here at the bottom, though. That would just be saying, hey, plug in 1 for I, and then move on to the next number, the following number, until you get to this number using whole values there. Those are going to be real numbers. I'm sorry, my whole video is in the way. Using the natural numbers, as I was saying, only whole numbers here. You start at the given value, and then you go through each whole number until you get to the value it tells you to stop at. Okay. But the summation just means take each of those numbers and add them up. So that's where you see I'm getting those from. So like this one here, if I look at this summation, it's going to equal 10. Now, please understand if you get on the homework and there's one that you're not sure about, just make sure you message me. It's good to kind of just make sure to see where it's coming from. It has applications, but the way I look at it for our particular course and the time remaining and what we need really to get to, I just want to do a brief introduction. What you'll see here, though, is if we put that summation together with a limit, all right, that's going to help us build from an exact area using this, but now we can go to the definite integral. All right. So remember, the definite integral is going to have boundary points where that indefinite, you're just trying to do an antiderivative. Okay. Now make sure you see here, though, that focus of what it's talking about. So let me see if it'll let me zoom in for you. Down here, you'll see it's saying delta x goes to 0. Okay. The one thing I would point out here, though, is as I mentioned, these are just coming from rectangles. So a length times a width. And you'll see right there, it's telling you it's rectangles. The width of those rectangles is what is being connected to delta x. And the idea behind this, what we would eventually call a Riemann sum, is that as those rectangles get so narrow that delta x is approaching 0, the number of rectangles will grow. And that's where this little piece you'll see here says into infinity. What if we can get an infinite number of rectangles in there? And those limits are what allowing us to go and say, hey, I can use this definite integral to get the exact area. Okay. So the idea behind all this, just to sum up what I'm saying, is that we can use a definite integral to get the exact area. In order to do so, though, make sure again that you see our function must be continuous over the interval we're working on. That's definitely important. The non-negative stuff, technically we can talk about that, but from this definition, it's being specific. For this to work setup wise, we'll get there. There will be a couple, though, we need to look at what happens when the negative aspect comes up. The continuous, though, has to be in place. Okay. Now, with that said, what I want to do is use this to show that, like, hey, how do I actually apply this now? Okay. So another thing that you might see come up on here that's definitely important is the fundamental theorem of calculus. So keep that in mind that this is going to piece that's very important. It's not just definite integrals. There's broader ways to use this. We're just looking at it from the definite integral perspective. What you'll see here for this example, though, instead of using the quadratic, I went to a line. All right. One of the things about the line, though, again, is if we really want to look at this, we could possibly use a triangle type approach. So keep that in mind if we wanted to check our results that we get here. However, I'm going to use this definite integral approach where we're saying, hey, once I integrate this, I go from the antiderivative or from the function, sorry, going from the original function to its antiderivative. We can evaluate that at the upper bound and the lower bound. That's where those are coming from. And then a quick subtraction will give us the exact area we're looking for. Okay. Now, the way that we'll work that out then is first recognize that that's a linear function. So lines are continuous, right? Only exception there would be a vertical line that we have to be careful of, but here we have one with a slope of 2, so we're good. That means we can definitely go in and evaluate this integral. So we'll say 2 times x squared over 2 minus 1x. All right. And what you'll see here, though, oftentimes instead of using parentheses, a great way to write this is using brackets. And we're going to keep the 1 and 4 on the outside of the bracket so that we don't lose what we're trying to find. Well, make sure you remember here, if this is f of x, this is our antiderivative, uppercase f of x. Now, with that said, hopefully you'll see here, we can clean that up a little bit by just saying x squared minus x. But the next step is, hey, I didn't want just an antiderivative here. We wanted to go evaluate this from the 1 to 4 boundaries that we were given. The part that you want to remember is when you go to this next step, you want to do the upper bound. Oops. So we'll do 4 plugged into our function minus the lower bound, the 1 plugged into our function. That's going to be one thing you want to make sure you're careful of. Like, hey, when it says f of b, it's antiderivative and then plug in the upper bound. F of a here is get the antiderivative and then plug in the lower bound. So I took this pattern, plugged in the 4, and I took the same pattern and I plugged in the 1. Now, with that said, we can go and just do our evaluation and order of operations. Like over here, see that you're going to have 1 minus 1. So that's just going to go to 0, which would just leave you with this piece here, which is going to be 16 minus 4. So when we evaluate this, we would get 12. Now, just to make sure to go and graph this so you see that where we're coming from. What we're saying here is the area that we were just looking for is right here. Now, one thing you do have to be careful of, this one doesn't give us a nice triangle or anything, but if you go through and cut like right there on that area, down here at the bottom, you can use length times width. So you'd say, hey, like that's 3 times 1 down here. And the upper portion here, we do 1/2 times 3, which is our base, and our height in this case would be what? 1, 2, 3, 4, 5. So you could break it up and use the geometry here. Just make sure you see that sometimes it's a little bit more involved. And then make sure go back to the previous example we looked at that said like, hey, we definitely need something more than geometry. Any questions or concerns though with this first example? When I'm looking at this, I don't think I counted correctly on here, but just use that idea of you could have broke it up that way. Now, one thing I do want us to be careful of when I look at this problem, let's go dig into it a little bit deeper before we do some more examples. If some of you may have noticed, I did not put the plus C here. Okay, so technically, yes, we're supposed to have a constant term here. Just make sure you see here, we know that we're going to go with this and do that f of b minus f of a. So anytime we're dealing with a definite integral where we know we need to do the subtraction, the constant term can be just left off. What you'll see here is when I got down to this step here, I would still have x squared minus x, so it would just be plus c. And when you go to do that subtraction, a lot of this is going to work out the same. So that's going to give me 0 here. Remember, this was 16 minus 4, so that's going to give me 12. So we'll have 12 plus c minus c. Well, hey, that piece equals 0. So understand that the reason I didn't put the plus c here at the beginning on that previous example is because when we're dealing with a definite integral, the two constant terms will subtract out at the very end. So you don't need to do that. That would just be extra work. Now, if you need to do it just so you don't forget, make sure you do it. The main thing, like as I mentioned, is always pay attention. Am I trying to find a definite integral or am I just using the indefinite integral for the purpose of an antiderivative? Okay. Well, you'll see here, those I got 2 more examples for us to walk through. Now, some things I would definitely point out here is always watch out for that continuous stuff. So like this first one, hey, that's a quadratic. So as far as being continuous, we're good to go. All right. The other thing here is that's going to be similar to the one that we talked about earlier. So it's going to have a y-intercept up here and it's going to go down from there. Okay. So with this one here, everything's going to be positive. So we don't have to worry about that either. However, when we look at this second one here, we do have to be careful. Okay. But just make sure you acknowledge the fact that, like, hey, x can't be zero, and I'm not even covering zero. My numbers are all greater than zero, which helps us with that aspect. I don't have to worry about it being discontinuous at zero because I'm not looking at that interval right now. We're looking at 1 to 8. That does not contain zero. Now, the other part that you have to be careful of as far as, what to expect from the integral, all those values will end up being positive for us. So we'll be good there as well. Okay. Now, as far as dealing with this, make sure you remember you always go to do your antiderivative first. So as we deal with this one first, we would say, hey, I get 6x when I deal with that constant term. And then I'll make this x cubed all over 3 since it was a exponent that I increased by 1. Just make sure you do not forget the upper and lower bounds that we're working with. From here, though, once we have the antiderivative, this is where we're just plugging in the values that we were focused on. Hey, I have a definite integral that I want to evaluate here. So I'm going to do 6 times 2 minus this 2 cubed all over 3. All right, that's just plugging in 2. I like to put parentheses or bracket around that. And then I'm going to subtract, plugging in the negative 1. So at that point, we have our f of b minus our f of a. And it's just about using order of operations to finish. Okay. Any questions before I finish this one? All right. So just doing some quick simplification here, we'd have 12 minus 8 thirds. This right here would give us -6, and this would give us plus 1/3. So we have a negative here and a negative there is where I'm getting the plus from. But then we need to distribute that to both of those. So we'll have plus 6 minus 1/3, which works out kind of nice because what you'll see there is we'll have 18 minus 9/3, which that's just 3. So altogether, this would be evaluated to just 15. The one thing I will point out is always be careful of the fact that we are subtracting here, so you have to distribute that to that entire second half of our definite interval. It's one thing that can get missed sometimes, so be careful. All right, so over here, make sure you see that with this 1/3, we were subtracting it, but then I have 3 negatives up here, so that's where it becomes a plus of 1/3. And then when I distribute the subtraction from here, it went from a plus back to a negative. So it does distribute to that. You have to be careful. It does get a little messy, especially when you have those exponents in there. Just make sure you double check and count out like how many I have. 1 negative, hey, 3 more negatives, it's positive. Then I brought in a whole extra negative. Okay, so they did flip around a lot there. And we did, like I mentioned here, that definitely was nice to happen because as we combined these, they already both had a common denominator of 3, and then 1 plus 8 gave us the 9. So that was kind of nice. Now, one thing I will point out again, though, is make sure you remember to start off like, hey, this is dealing with this, right? No, that had more to do with this. So remember, as you deal with stuff like this, anytime you have exponents, if you have like x squared, a negative value squared will always be positive. an x cubed. A negative value cubed will always be negative. So since this was odd, it ended up being negative, but I was subtracting. So because I was subtracting, that's where it became positive. It was a combination of those things. All right, so moving to the next one, though, make sure again you see the first thing we checked for was continuity. Hey, quadratics, linears, any polynomials. Hey, I know it's continuous. Things to watch for, x is in the denominator. Other things to watch for is like if I gave you the square root of x minus 3. Okay, make sure you remember like for radicals, we don't want that I involved. So we'd say x minus 3 has to be greater than or equal to 0. Those are kind of some things to be watchful for. Okay. Now, as far as dealing with this, for the second one here, it goes back to definition. We just have to remember that, hey, as I deal with this, the definition of a natural log of any value is going to be given from this integral. Okay. So by definition, this is what a natural log is. A natural log is given to us from an integral. All right. It's one of those things that I would point out to. We can go to more detail if we wanted to. I'm pretty sure the textbook does. But the one thing you definitely want to be comfortable with are some of those basic derivative integral rules, sorry, that we talked about. So like, why did I get this for these here? Make sure we're comfortable with constant terms and exponents. Make sure you watch out for this one here. Even if I write it this way, these two things are the same thing. Just kind of slide the dx to the outside and put a 1 up here. The other one to watch for that we have talked about is the integral of e to the ax dx equals, what was it, 1 over a, not e to the x plus c. Okay, that would be another one that we definitely want to make sure, some rules that we want to be watchful for. Okay. Now for this problem, then what we see here is I'm going to get from that to say this right here. If I need to, I can rewrite it, but that's going to be the natural log of x from 1 to 8. All right. One of the things that we will talk about a little bit more is technically it should be the absolute value of x because of natural log, we don't want negatives in there at all. But hey, we've already confirmed that we're dealing with positive values when we plug in. All those values are going to be positive, so don't even need to worry about the absolute value. Just make sure you see here though, and technically there's not much we're going to be able to do when I go to that subtraction part. I'm going to plug in the 8 minus plug in the 1. Just make sure you watch out for stuff like this. So the natural log or any logarithm of 1, remember that always equals 0. So here we'd find, hey, it's just the natural log of 8. So as long as we can get to that antiderivative, all we do is plug in 8 and plug in 1 and just make sure to remember this rule for natural logs. Any questions or concerns here? All right, so here's another little application example for us to take into consideration. It says Pure Water Enterprise finds that the marginal profit in dollars from drilling a well that is x feet deep is given by p prime of x equals the fifth root of x, and wants us to find the profit when a well 250 feet deep is drilled. Some things that we definitely want to be comfortable with is watching out for terminology. So make sure you see here, the second we see the word marginal profit, we should not be surprised to see a derivative notation here. That, hey, the function I give represents the first derivative of the total profit. Now, we can go through and do an antiderivative. Once we get the antiderivative, plug something in to get there. But the nice thing about this, one of the things that this definite integral helps us with is get to the answer we need in a more direct path. It also opens up some different stuff as well, right? What if you have a well already drilled and you want to increase the depth, right? So there's different ways that we can use a definite integral that just plugging into a function would be able to do, right? So if we wanted to, we can use this function here to go get P of X and then plug in 250, and that would give us the answer we're looking for. Okay, but the definite integral will take care of that for us. Just make sure you see here, we're starting off with a brand new well, so we're going to be digging from 0 to 250 feet, and we're given the marginal profit is the fifth root of the value X, right? Just make sure you see X is how deep the well is. Okay. One thing I will point out is don't ever forget your differential. That's telling us what variable we're focused on. Okay, it's definitely an important piece. And as we looked at for the summation approximations are there, that's what's kind of setting like, hey, all my rectangles, the width we're focusing on is going from left to right. Now, one thing I would encourage you to do here, though, is make sure you remember that for radicals, it's helpful to use rational exponent notation. Okay. The other thing I'd point out here is from 0 to 250, we don't have to worry about any restrictions for radicals, even though with the fifth root, negatives are fine. But since we're focused on just positive numbers, we're good for the continuous aspect. All right, so we have continuous function, all positive numbers we're plugging in. I can just jump in here and deal with it. Okay. Just be careful here when you deal with your integral here. Make sure you remember it's 1/5 plus 1 all over 1/5 plus 1. Okay. Don't have to write this stuff out. Just want to make sure we see where I'm getting my values from. When I deal with that, though, 1 is just 5 over 5. So what we'll have here is x to the 6/5 all over 6/5, 0 to 250. And I would actually encourage you to go one more step and say 5/6 times x to the 6/5. Okay. Is there any questions or concerns though with the antiderivative perspective of our integral? Just remember the idea is for a derivative, we use subtraction, right? So technically we would have went to a downwards direction, but since we're doing an antiderivative, that's why I added one here. So be careful as you're studying for next week's final that you're going through your rules and reminding yourself, hey, I use this one for this situation and I do the opposite for this situation. Okay. With that said, once we get here, we have our antiderivative in place. We can go ahead and plug these values in. So I'm going to plug in the 250. We'll plug in the 0. The nice thing about the 0, though, oops, that whole term's gone when we plug in 0. So that's kind of nice. Which, if you look at the antiderivative perspective, I just plug in 250. That's what we were looking for anyways. Okay. But this is definitely a situation where let's go round it to the nearest whole foot. No, sorry, we're doing this is going to be the profit. So let's round to the nearest dollar. 250 feet is the depth that we're at. So the profit here would be $629 for digging the depth of the well to 250 feet. Any questions over getting to there? All right. The one thing I would point out then is just make sure you see here that the profit function we got just now is the antiderivative of what we were working with. The big difference here is technically we would have a plus C, right? That plus C definitely impacts what we're working with. What we see here for our problem, though, is we didn't have to worry about the plus C because remember, that would have gotten subtracted out. There would have been like a plus C here and then a minus C here. So that's why I didn't worry about it here. So that's why we have to be careful with how we handle it. The definite integral definitely took away some complexity there for us going through this work to get exactly what we wanted. Okay. The other thing I would point out here too is, this is the idea that you're drilling a brand new well. Okay, what if someone wanted to take an existing well and increase its depth, right? So you might have a situation where it's like, hey, we have the, 100-foot well that we need to increase its depth. So what is going to be the expected profit from a well going from 100 feet to 250 feet? All we're changing there then is, hey, I'm going to go through here and change all these zeros to say 100. So that would have an impact on our work for us. Now, as I mentioned, I know I'm going through this a little bit quicker, right? Um, if you get stuck on that approximation stuff, please just make sure to reach out to me. We'll do our best to clear up anything we can. I think it's helpful to kind of know what's out there. As far as this course is concerned, though, I definitely want us to be comfortable with finding antiderivatives as well as dealing with the definite integral. So the two different things that you'll see in the book are indefinite integrals and definite integrals. These right here are what we call definite integrals. There is a boundary set in place that we're using to help evaluate what we're working with. The indefinite integrals are used mostly for just, hey, I need an antiderivative. Let's use this notation to help give us something to work through as we deal with it. Okay. The other thing I'm going to point out, we'll go into more on Wednesdays, that not every integral is something we're going to be able to evaluate given the techniques we're going to talk about, but really in general, not all integrals are solvable. Okay, as far as derivatives are concerned, we can find ways to work through it, but when it comes to integration, that may not always be the case. Okay, so please keep that in mind. Approximations, as we saw with that limit definition, are very important when you get an integral, that's going to be our best option, is using an approximation. Okay. But if you don't have any further questions or concerns, I think this is where we're going to stop at today. I will be working on the practice final stuff as best I can throughout the week. As far as class on Wednesday, the plan is to have it face to face. Okay, just keep an eye on the announcements, of course. But I don't foresee not being able to be there face to face on Wednesday.
I have a question about the homework. So
Uh,
I think we have four posted on calendar today, but I'm looking at my grades right now and we still have 10 left. Do we have to complete all of them, or just the four published on calendar?
what are the ones that you're saying that's showing that are left to complete?
Section 3.4, section 3.5, 3.9, and 3.6, 3.8. I'm only seeing 4.1 to 4.5 on the calendar of things that need to be
Yeah, so
completed.
4.1 through 4.5 was the stuff for the integration that we're looking at right now.
Yes,
The
due
other
this
one
week.
is from the stuff that I didn't, I'm sorry, I didn't auto sync this. This is probably why you didn't see it. Now, my main thing is just as far as the homework is concerned, make sure that you're going through working on this stuff right now. I've opened it up to where you should be able to access any of the homework assignments up until next Tuesday. So if
Okay.
there's any homework assignment that you need to go get complete, you have until next Tuesday to do it. Okay.
Okay. Okay. Thank you.
Um, as also I mentioned, though, keep in mind that we're preparing for the final. So make sure as you're dealing with stuff like, hey, all this is for focusing on something that could be on the final. Okay. The homework is what was it, 10 or 15% of your overall grade? I'm not on my computer at work. I'd have to do that at work. I don't remember right now. So keep that in mind as you're dealing with that. Don't stress yourself out to go finish those assignments because it looks like just the way I published them. If I remember right, when I went and looked at our class, I had set due dates, but they didn't get assigned. So I had to fix that this morning.
Yeah, because the 3.4 and 3.5 on Canvas, it said to be due on November 14, but when I clicked on it, it said due December 7th.
Yeah, so everything at that point, that's how I corrected it. I just extended the due date. Okay, there should be no consequences for working past the quote unquote due date for that. But there is the final deadline is the day before the final. Okay, so keep that in mind. Any other questions, concerns as we finish up? All right, then thank y'all for your flexibility. Y'all have a great day. And like I said, I should see you in person on Wednesday. So have a good day and see you Wednesday.